In this video, I'm just going to do a few examples of graphing rational functions because some students sent me emails asking questions and just kind of wanted me to work through a few more of them so they could see all the steps to working them out. So, first off, suppose we have some rational function f of x equals x squared minus x minus 6 over x cubed minus 9x. The first thing I do with a rational function, which is essentially whether it's a rational function or a quadratic or pretty much any polynomial or rational type thing, factor it, simplify it, put it in lowest terms, do whatever I can to make it easier. So start by factoring this. The top is a quadratic. So two numbers that multiply to negative 6 that adds negative 1. That's minus 3 and plus 2. On the bottom, first factor out the common x. Then I'll be left with x squared minus 9. Which will then be a difference of squares, x minus 3, x plus 3. And I'll get this out of the way so it doesn't confuse me later. Now, once I have it factored, now I put it in lowest terms. And in this case, cancel out the x minus 3's. And I'm left with x plus 2 over x times x plus 3. And one thing you can note now, because we'll use it later on, once it's in lowest terms, figure out the degrees. Here, the degree on top is 1 because it's linear. The degree on the bottom is 2 because that's an x squared if I solve it out. Now I want to graph it. And as far as it goes, there's really just like 7 steps to my graphing here. And I'm going to run through each step and then ultimately we'll plot the graph and see what's going on. And then, like I said, we'll do another example after. So first off, I need to see if there are any holes in my graph. We get holes in our graph in places where the function is undefined, but that undefined term gets canceled out of my function as I work, which sounds a little bit confusing. All it really means is any factors that cancel, numerator and denominator, top to bottom, will result in a hole in my graph. So in this case, x minus 3 cancels, which means x equals 3 will give me a hole. And all we really do is we'll do the entire rest of our graph, and then at the end of our graph, we'll just draw a hole wherever the function is graphed when x is equal to 3. So we kind of do that at the end, but we find it at the beginning because we see it from the factoring. Next up, VA, vertical asymptotes. Vertical asymptotes occur where the function is undefined in lowest terms, which means zeros once I factored it out in the denominator, because that's where this will be undefined. Clearly it's undefined when x equals 0, because that will give me 0 in the denominator, and it's undefined when x equals negative 3, because that will give me 0 in the denominator. Next up, I want to find the zeros of the function. Zeros occur where the fraction, the rational function, is 0, which are zeros in the numerator. So here that's at x equals negative 2. The next thing we need, and sometimes we use it, sometimes we don't, it varies, is the y-intercept. Essentially, when it comes to graphing these, sometimes you need an extra point or two to help you connect the dots, like with our polynomials, and the y-intercept is a good one to use. Other times we'll use other points. But to get the y-intercept, we set x equal to 0. The problem is here, if I set x equal to 0, the denominator is 0, which means it's undefined. Which means there is no y-intercept. Which again, really just means from a graphing perspective, which is why we care, if I need to find an extra point, I can't use the y-intercept, so when I'm graphing it, I'll just pick some other point randomly. Essentially, I'm just going to use something to help me connect the dots. The last thing I need to know is if the function has a horizontal or oblique asymptote. Which from here on out, I'll just call H or OA, so I don't have to write all that. And the way it works is, we look at the degree in the numerator and the denominator. And the rule is, if the degree in the numerator is less than the degree in the denominator, it's a horizontal asymptote at y equals 0. If the degree in the numerator is equal to the degree in the denominator, it's a horizontal asymptote at y equals the quotient of the leading coefficients. And if that's a little weird, we'll do another example after this so we can see it. And if the degree in the numerator is greater than the degree in the denominator, it's an oblique asymptote, which you find by long division, which is why we studied long division before this. And you can use the polynomial long division or the synthetic division, obviously. But here, the degree in the numerator is 1, the degree in the denominator is 2, the degree in the numerator is less than the degree in the denominator. That's this one. So it'll be horizontal at y equals 0. But now with that, I guess there aren't 7 steps, there's only 5. Maybe a 6th step if I had to do the long division. Now I should be able to graph it. And let's see. The whole, I can worry about that at the end. The vertical asymptotes, I'll have one at 0, which is hard to see because it's right along the axis, but I'll draw it. And I have one at -3 over here. I have a 0 at -2. If that's -3, we'll say that's -2 right there. I don't have a y-intercept, which makes sense now because the function is undefined there. There's an asymptote. And I have a horizontal asymptote at 0. Which again, I also really can't see that because that's along an axis. And now, with that much information, we should be able to graph it. And that's kind of the point I was making earlier, why we use the y-intercept or some other point. I really can't tell what's going on with that graph right there. But generally speaking, if you can't tell what's going on, pick one more point and then you should be good. And you can pick any point you want. In this case, I'm just going to let x equal 1, maybe right over here. Because that's a nice round number. And just plug it in. If x is equal to 1, I get 1 plus 2, which is 3, over 1 times 1 plus 3, which is 4, I get 3/4. So when x is 1, I get 3/4. In all things being equal, that doesn't have to be really accurate. I really, for the purposes of this, just care if it's positive or negative. If the y value is positive or negative. Because now I can just use my understanding of what's going on. If I'm at this point, if I go to the right, ultimately I go up or I go down. Eventually, I have to approach my horizontal or oblique asymptote, which means in theory, I'm not really concerned since you don't have access to a graphing calculator with these being incredibly accurate. Ultimately, even if I go up a little, I have to come down to that asymptote. So whether it looks like this or that, I'm pretty much okay with. We'll go with this one because I don't necessarily know that it increases. But then the question becomes, as I approach the asymptote, do I cut through it or do I hit it? But if I hit it, that would give me a 0. But I've already plotted the zeros. I only had one of them, which means I can never touch that asymptote, which makes sense. That's why I just approach it, because I can never touch it again. Over on this side, again, the same idea. This is a vertical asymptote. Even if I went down a little, I could never hit 0. So the only thing I can do is shoot up here and never touch that asymptote. Now, we have to look at the behavior around the asymptote, and the way it works is, you look at the particular factor up here that gave that asymptote. In this case, it's the x. You look at the degree of that. This is degree 1, this one's degree 1, this one's degree 1. And the way it works is, if the degree of the asymptote, the factor, is odd, then the sign around the asymptote switches. If the degree was even, the sign would remain the same. Meaning, on this side of the asymptote, either I have to start up here at infinity or down here at negative infinity. Since the degree here is odd, the sign switches. To the right of the asymptote, I'm positive, which means to the left of the asymptote, I have to be negative. So I start down here, but I have to come up and hit my 0. Now at my 0, I use my rules for polynomials. Do I cut through the axis or bounce off? I look at this factor, which gave me that 0. That's odd degree. Odd degree means cut through the axis, so I cut through. And now again, I have essentially the same question over and over. If I go up, I can eventually come down, but that would give me a 0 that I don't have, so I can't go down, which means I go up. And then I just approach this asymptote like that. Around this asymptote, I then do the exact same thing. I look at the factor that gave me the asymptote, it's this one. I look at the degree, it's 1, odd, which means the sign around the asymptote switches. On this side it's positive infinity, which means on this side it has to be negative infinity. Now I come up, eventually, if I keep coming up, I hit the axis. That would give me a 0, which I don't have, so I can't do that, so I'll just approach it. And there's my graph. The last thing I have to do, which frankly is the thing I usually forget, is to put the hole there. But here, we'll remember at x equals 3. This was where x was 1, so I'll just arbitrarily say that's x equal to 3. And I draw my hole. To a certain extent, yes, there's a lot of different things going on. The good thing about these is there's really only one way to graph them. Meaning, the rules only work one way. I can't cross the axis again because that gives me a 0, which I don't have because it's not listed there, which tells me I have to approach it. Little things like that make your graph look the way they do. It's only when you start kind of randomly breaking rules, now I'm going to mess up my pretty graph. Oh, I'm going to go down here, then up here, and yeah, look. But then just thinking about it, oh, I gave myself zeros that I don't actually have, because if I had them, they'd be listed right there. So as long as you just kind of learn the basic rules, this is pretty straightforward. But we will do one more. These take a while, so the videos tend to get rather long and involved. Okay. So suppose we have f of x equals x squared plus 6x plus 9. Why did I do that? Over x squared minus 4. First thing I do, factor it. The top is a perfect square. It's x plus 3 squared. The bottom is a difference of squares, x plus 2, x minus 2. Nothing will cancel out to put it in lowest terms. So then I just look at the degrees. The degree on top is 2. The degree on the bottom is also 2. Now I start listing out all my information. So first, I look for holes. Holes occur with factors that cancel out to put it in lowest terms. Nothing canceled out, so there's no holes. Next, I look for my vertical asymptotes. Vertical asymptotes occur where the function is undefined in lowest terms. Those are the zeros in the denominator, which are just 2 and negative 2. Next, I look for my zeros. Zeros are where the function is 0 in the numerator. That's what makes the fraction 0. That's x equals negative 3. Then I look for my y-intercept. Sometimes it exists, sometimes it doesn't. It's just a help for us. To get the y-intercept, set x equal to 0. On the top, I'll get 0 plus 3 squared. On the bottom, I'll get 0 plus 2 times 0 minus 2. 0 plus 3 is 3 squared, which is 9. 0 plus 2 is 2. 0 minus 2 is negative 2. 2 times negative 2 is negative 4. So my y-intercept is x equal to 0, y equal to negative 9/4. And again, ultimately, I really care about the sign of that because it's above the axis or below the axis that kind of dictates what happens with everything else. And then lastly, horizontal or oblique asymptotes. Like I said, I'm abbreviating, writing all that out. To determine that, I look at the degrees. Here it's degree 2 over degree 2. They're the same. So if the degrees are the same, it's a horizontal asymptote at the quotient of the leading coefficients. And what that means is, I look at my original function. The leading coefficient is x squared. That's a 1. The leading coefficient here is x squared. That's a 1. So my horizontal asymptote is at y equal to 1 over 1, the quotient, which is obviously just 1. Now, I should have enough information to graph it. So, no holes to worry about or for me to accidentally forget at the end. Vertical asymptotes, one at 2 and one at negative 2. I have a 0 at negative 3. And I have a y-intercept at 0, negative 9/4, which I'll say is right there. And then I have a horizontal asymptote at 1. And now graph it. And again, here you may get the same idea from the last one that, okay, no, I don't know what to do and I don't have enough points and all of that. But pick the y-intercept right here. If I go to the right, I either go up or down. If I go up, I eventually hit the axis, which would give me a 0, but I already found the zeros. It's only there. Which just tells me I can't go up. So I have to go down. And then eventually I approach the asymptote. And again, I do stress here, because we're not using graphing calculators, and this is only pre-calc, could this look slightly different? Could it maybe go up a little, then come down, something like that? Yes, here we're just getting a rough sketch of the graph, so don't worry about details like that. In calculus, we'll have more advanced tricks we can use to expand on this. But now, well, let's see. At 2, I look at the degree of the asymptote to see what I should do. For 2, that's the factor x minus 2. That's degree 1, which is odd degree. So the sign switches around the asymptote. Here it's negative infinity, which means on this side I have to be positive infinity. Now I start coming down, and, well, I can't go all the way down to the axis because, again, if I did, I'd give myself a 0 I don't have, but that makes sense because that just means I'll approach my asymptote, which is why I never hit 0. Here again, I do stress, in theory, you could go below the asymptote and then come back up to it, as long as you don't hit 0. There are tricks we can do to test that, which I won't go into right now, but ultimately, you have to approach your asymptote. Over here, I do the same thing. If I go up, I'll hit 0, which I can't do because that'll give me a 0 I don't have, so I go down. Now here, I use the degree of the asymptote again. At negative 2, that's degree 1, which means that's odd degree, so I switch the sign around my asymptote. This is negative infinity, so here it's positive infinity. Now I come down, and I guess in this case, I have to hit my 0, So here I will go through, but then at -3, do I cut through the axis or bounce off? X plus 3, well, that's a degree 2. For polynomials, we said if we have even degree, we bounce off the axis, which makes sense. Then I come back up, and then I'll approach my asymptote. And again, kind of the point I was making earlier about these things have to work a certain way. If I randomly cut through the axis, I would ultimately have to come back to my asymptote because I have to approach it, but that would give me a 0 that doesn't exist, which means I can't do this. It only works if I bounce off the axis and go back up to the asymptote, which is exactly what the rule tells me has to happen. So there's kind of a common sense way of doing this, and that's how the rules actually work, which is good. And there's my graph, and like I said, thankfully there's no holes to worry about. The last thing that maybe we'll quickly go over, because I know this video is too long, if you want to know if you're actually going to touch this horizontal asymptote or not, here I clearly do. All it really means is your function crosses the asymptote, it intersects it, going all the way back to our equations of lines. That means they're equal to each other. So set them equal. X squared plus 6x plus 9 over x squared minus 4 equals the horizontal asymptote, which is 1. Solve that. Cross multiply, this is 1 over 1. I get x squared plus 6x plus 9 equals x squared minus 4. If I solve that, subtract the x squared over and it disappears. So I'm left with 6x plus 9 equals -4. Subtract the 9. Minus 4 minus 9 is minus 13. Divide the 6. X is -13 over 6, which is -2 and 1/6. What that tells me is my graph crosses the horizontal asymptote at x equal to -2 and 1/6. Well, here the x's are positive, which means I never cut through it and come up. I just approach it like that. But this was x equal to -2, so -2 and 1/6 is a little more to the left, which is exactly what we got right there. It also tells me that over here, I don't come above the asymptote and then come back down. I have to just come up and approach it, because according to this, I only cross it once. And again, the point, we did all of this quick algebra to find where it crosses. But just graphing it, our understanding of zeros told me I have to come down and cross it because I had to hit my 0. And our natural logical reasoning agreed with what the math actually gave us. So there is a way to just kind of see how these things have to work, and the math will agree with it. So keep that in mind. Again, if you randomly just start, I'm going to mess up my pretty picture here, but if you randomly shoot down here, then up here, then we go over there, well, look, I gave myself a bunch of zeros, and I don't have those, and so I've kind of messed everything up. As long as you kind of stick to the basic logic that we understand, these graphs work really well. If there are any other questions, feel free to let me know, and I will make more videos going over whatever you have questions on.